Okay, so good morning. I think in last class we discussed the theory behind linear regression. We saw how it works. We saw, maybe let me recap a few things. We started with explaining that regression is a different kind of problem than classification. The primary reason is that the target variable or the target class, the target label, is not a categorical value, but it's a continuous value. So instead of having fixed number of target classes, we have infinite number of target values that can take place. So primarily that means that we have to look for a different kind of way of solving the regression problem compared to the classification problem. Within this regression problem, we looked at a simple method called as linear regression, which basically says that our hypothesis function, h theta or y, is equal to theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3, and so on till theta d xd, if the problem at hand has d dimensions. It's basically a weighted sum of each of the dimensions, and these weights are theta 0, theta 1, theta 2. These are the parameters of the model, which decide how much how much important a certain feature is in predicting the target variable y. So that is our hypothesis equation. Further, we said that we need to have a measure that can help us to see how close or how far we are from our answer. And for that measure, at least for this case, we use something called as the mean squared error, which we also call as a cost function. So our cost function j theta or mean squared error is given by 1 by 2n summation of summation over the variable I going from 1 to n. And within that, we evaluate the square of this subtraction, which is h theta of xi minus phi I. So that is h theta of xi is our prediction. We subtract from that the actual answer, the actual label which we know to be true, yi, and the error, we will square it, sum all of them, and take its mean value. And then we have an additional 1 by 2 so that it will help us in gradient descent. That gives us our cost, which can help us to see how good or how bad we are doing with respect to our prediction. And then finally, we say the task of linear regression, or for any machine learning per se, is basically to reduce the cost. By changing the values of theta, by updating the values of theta, we want to reduce the cost to a point where we reach the minimum loss. In which case, we said we can take help from gradient descent, and gradient descent would help us to find out how should we change the parameters of theta so that our cost goes down. And for our case at linear regression, our gradient descent can be evaluated as, or the step taken by gradient descent can be evaluated as so far as then updated value of theta is equal to the old value of theta minus alpha times the gradient, that is the partial derivative of j with respect to theta. Okay. And the alpha here controls the learning rate, which helps us decide how fast or how slow we want to reach to the minimum value. If we are too slow, it will take too many iterations. If we are too fast, we may probably diverge. So we have to come up with a balance of alpha. And these are the different things at control. And with that at hand, let us look at some code today where we will try to implement from scratch how linear regression can be used. Okay. So let me continue here. So the notebook, we first start by loading some basic packages. So we use NumPy. Of course, we have to use NumPy for our linear algebra and for our implementation of calculus and so on. Going ahead, we also load a data called as the Boston data, which is one of the sample data that comes with scikit-learn's datasets. And the Boston data is basically a housing price data. And this is a simple version of it. And maybe once we have done through this, we will explore in detail the housing price 81 column data. And that is something that we'll use a few classes on that after we have finished this. But for now, since we just want to test linear regression, We're just taking some data as you know, it doesn't matter what the data is. Let me load the data. From this data, I can extract dataset.data, which is my X, that is the predictor values, and then dataset.target, we take into Y, which is a target variable. And we see that our samples are 506. So out of 506 samples, we have to learn a model and do something about it. If I do a shape here, I can see that there are 506 rows with 13 columns. So those are the 13 features that we have. And then we have one target variable that we are trying to. If I look at data set and I print out the description, we see some information regarding our data. So it says that there are 506 instances or data points, 13 attributes, which are numeric or categorical in nature. Okay. And these are those attributes. That is the per capita crime rate per town, proportion of residential land zoned for lots over 25,000 square feet, proportion for non-retail business acres per town, and so on. So we've got lots of information here. Our focus is not to focus too much on, or our agenda is not to focus too much on the data for now. We are more interested in the algorithm and implementing the algorithm. Okay. So we've got some data. We say that, okay, there are no missing values, which is great, because then without any pre-processing, at least in this case, without any pre-processing, we can pass all that data to our algorithm. And let me go ahead. These are some of the formulas that we'll be using. Our hypothesis equation is y is equal to h theta of x, which is this implementation, whose summation form looks like this, and in the vectorized form looks like this. So x times theta, where capital X is basically a matrix in which the rows, each row represents one data point, and there will be 506 rows for our data. Theta will be the parameters of the model that we are trying to train. Our cost function looks like this, which is basically the mean squared error, half of the mean squared error between our prediction and the actual value. And its vectorized form looks like this, which is 1 by 2n x theta minus y transpose multiplied by x theta minus y. Then we have the gradient descent update. So gradient descent update is the new value of theta is old value of theta minus the learning rate by this term. This term is basically the gradient of j with respect to theta j. And if we have to write this in the vectorized form, we come to this part where now we are not just updating one parameter, we are updating all the parameters in one go. We also saw the criteria for convergence is this, whereas the L2 norm here, that is the 2 bars and the 2 here, can be evaluated using this formula. Okay. In our case, we will not be using the convergence criteria for stopping. We will be using the total number of iterations that we want to run this model for, just so that we have more control and we can see how fast and slow things are moving. Let's go ahead. These are some of the feature names. And what we could do is we could put that into a pandas data frame so that we can see how things are. So we are importing pandas as PD. PD.data frame X is the data that we want to load, and the column names are given by this thing. If I execute this, you can see that, okay, we have 506 rows with 13 columns. This is what the data looks like. We want to do a simple describe on this so that we can see basic statistics. Let's do that. So if you df.describe, you can see that CRIM has a mean of 3.6, a standard deviation of 8.6, and a range from 0 to 88. Okay. Yeah, 0 to 88.96. So basically that tells me that there may be an outlier here, because if my mean is 3.6 and my standard deviation is this max value seems out of place, but that's fine. as I said, we're not focusing too much on this data right now. But it just helps me to see that minimum maximum is 0 to 100, 0 to 27, 0 to 1, 0 to 0.38 to 0.87. So this data tells me that there is definitely a need for feature scaling because many features are in very different ranges. And when they are in different ranges, we saw that gradient descent will take a lot of iterations uh, to reach to the final point. So it would make sense if we could standardize the values and then. So let's see the number of samples. We take that into n samples. We find the mean and standard deviation for all features. So I'm just running through a loop. Uh, I evaluate for the entire X, I evaluate mu and sigma. Mu is mean of each of the columns. So here when I put 0, what I mean is basically for this data, I want to look at each column and then for that column find out mu and for that column find out standard deviation, and then I want to print all of this data using a for loop. So when I execute this, I can see that this would match with my model here. So mean is 3.6, standard deviation is 8.6, and we can see, okay, that's true. And then it goes through each of the columns, and we have mean and standard deviation. So we can see we've got a lot of variance. Okay, see even here we have lots of variance. So let's standardize it. So very simple idea to standardize. I'll say the new updated value of x is the old value x minus the mean value. So that will give me 0 mean divided by sigma, that will give me unit standard variation. So when I execute this, and now we look at the mean and standard deviation, you can see that all means are close, very close to 0. All standard deviations are 1. So we have reached our reached our data, or we have scaled our features so that each of them are giving equal importance to the model. So now this is what our updated X looks like. This is our shape. And for linear regression, if you remember, there is a bias term theta 0, and the theta 0 needs to be multiplied by x 0, and x 0 will have all values of 1. So in this case, we are adding that. So to these 13 columns, we are adding an additional column of as many rows as the data is there, and the new value of x, so that we will have, you see here, first value of every row as 1. Okay. And now if I look at its shape, I can see that, okay, there are 14 columns instead of 13 columns. So this additional 1 will help us to convert our equation in matrix form rather than defining it in the base, rather than evaluating using summation over for loops. We can, with this one, we are now having the advantage of using matrix multiplication. Okay. Going ahead, we can see that this is our cost equation, and this is the linearized, or what do you say, vectorized version of our cost equation. So we say, let me create uh, a function like called as compute cost, which will help us to evaluate this term. You say, okay, the number of samples is length of y. This part, which is the hypothesis equation, can be evaluated by doing something like this. I can say h is equal to x at the rate params. Do you remember what this at the rate stands for? Any of you remember what this at the rate stands for? If you go back to our NumPy classes.
No, Raj, I don't remember.
Okay. At the rate stands for matrix multiplication. So either we can use at the rate, or the other option would be something like this. We could use x dot of params, and that would also help us. Percentage should be percentage is comment in MATLAB. Okay. So this would also help us to give dot product between x and theta, so that we can have the cost. So we're simply doing x at the rate params, which is matrix multiplication between these two quantities, so that we get our h. Now, for this part, I am using this. I'm saying, okay, the mean squared error can be evaluated by h minus y whole square, the sum of all these terms, divided by 1 by 2n. Okay. So we have done some kind of vectorization here, but every other part we are not doing vectorization. We are just using this formula. Okay. Even though I'm not writing a loop, I'm using NumPy's method, which I think interior it definitely is using what do you say, uh, some kind of optimization in matrices, but I'm not forcing it to happen. Okay? I'm not using this one. So this is one way that I implement this function. Let's compute cost. Now, if I just want to see how much time does it take to evaluate uh, compute cost to get the answer. Okay. So I just wanted to get an idea of when I implement the code like this. That is, I'm using NumPy's summation of some method to see this, and I execute this. I have to first execute this part and then this part. Okay. So I can see that I get an average of 25 microseconds. Uh, so what this code will do is when I put time it here, this code will be implemented many times. So in this case, it is implemented or it is executed 10,000 times. And of those 10,000 loops, okay, sorry, it is executed 7 different times, and each time we have 10,000 loops, and it gives us, for those 7 runs, it gives us what is the mean time it took and what is the standard deviation. So this code, the compute cost code, roughly executes in 25 microseconds, plus or minus 6.54 microseconds per. Okay. Now I implemented the same thing using this part, which is the compute cost vector, which says, okay, h is fine. To evaluate j, I said it is simple. We do h minus y transpose matrix multiplication with h minus y and this part. Okay. And then we return the cost. So when I do it this way, and then we look at the time, we let it execute. Okay. We can see that it takes 13.9 microseconds with 150 plus or minus 150 nanoseconds per. So just by writing the equation, instead of writing this part, if we write it this way, which is basically taking advantage of this matrix multiplication to get the square, then we are getting at least roughly half the time that it takes to run this one. Even this one, we have actually used matrix multiplication here to get our job done. Had we not used that, had we done something more expanded, it would have taken further longer. So this is just a note on, we spent some time defining these terms of matrix multiplication, transpose, and dot products, and so on. So there is advantage to using it that way, especially when we want to use costs and gradient descent at every iteration. Then it makes sense that we do things fast.
Small doubt.
Yeah.
In step 21, why we are returning J00?
This part. Okay. So here we are interested to evaluate cost, and this multiplication, interestingly, returns to us a 2 by 2 matrix. Okay, with only one value. A 2 by 2 matrix with one value, and since we want, so I'll explain in the next part where we are using this. It will be used within our gradient descent part. So I don't want a 2 by 2 value which is having just one number. Okay, so I'm just taking j0 of 0, so that becomes a normal value. I'll show you. I'll show you what this means. Yes. Yes. So my point was, even going to something like this. So now it does not make a difference, right? We see that, okay, 25 microseconds, 30 microseconds. does not make a lot of difference if we go either of them. They both are very fast. But when we move to something called as neural networks, we'll find that we would be wanting to use gradient descent a lot for each of our nodes. And neural networks is generally a very hard problem because we'll be having thousands of input nodes, multiple hidden layers, and many output target variables. And at each node, we want to implement gradient descent. Then uh, we need to save every microsecond that we can save because that will make a lot of difference in the final time that it takes to train your model. So implementing in linear algebra is thus important. Let's go ahead. We are also looking at the gradient descent update term, which looks like this. And this is how we would be implementing it. So the gradient descent, again, I'm writing as a function, which takes x and y as inputs. X is the your features and attributes. So in our case, the 14 features and 506 rows. Y is the target that we want to estimate. Parameters are what we will be changing, and we'll be tracking how it is, how the cost is varying based on this. We have learning rates that can help us to control how fast or how slow we are reaching towards our minimum point, and we have number of iterations of the model. So we see here, we start with, let's take the number of samples. Let's start with J history. So this is actually not a required step, but this step of storing the cost at every step will help us to see if our model is having any issues or not. Okay, especially dealing with the learning rate alpha. Is our alpha too high or too low? Our cost J can help us. So what we'll do is every iteration we will try to store the value of cost so that we have some idea of how the model is trained. Further, we'll implement this for n iterations. As I said earlier, we are not going for the convergence criteria. In our case, we'll be writing how many iterations we want our gradient descent to work, and for those many iterations, we will operate. So for each iteration, we'll say update the new value of parameters is equal to the old value of parameters minus alpha by n, which is this part, alpha by n, and then we have this term. And we had already seen that the linear regression form of this, or the vectorized form of this term is basically x transpose, the x transpose. So this is matrix multiplication with this term, which is again x times theta minus dot. Okay. So implementation is very simple, especially if we can do matrix multiplication. Then we implement the update value, and then for that update value, we compute the cost. So let me, instead of compute cost, let me use compute cost vect, which is a faster term, and I give x and y and params, and that gives me the cost back as j. And then I store that for that iteration. And once we finished all iterations, we'll return the entire j history, and we'll return the latest value of parameters. So let me execute this. So now we have everything ready. We just need to implement and see how things work out. Before going there, let me show you the cost value. So let's say we start here. Let's say we'll go for 50 iterations with the learning rate of 0.1. The number of features are here, x. We have to start with some value of theta, initialize some value of theta. In this case, let us initialize theta with all zeros. So how many zeros? As many features are there. There are 14 features, theta 0 to theta 13. So 14 features. For 14 features, we'll update all values as zeros. And let us evaluate the cost at this point. So when we evaluate the cost at this point, we get 296.07. And if we evaluate the cost using our vectorized term, we see that this also has 296.07. Let me remove this part, execute this, and give the answer here. So now we see that, okay, we have the same answer, but this answer is basically a multi-dimensional array. And what I need is I need just one number. Okay. So what I could do is I can say, okay, whatever this answer returns, if I go for 0 column and 0 row, then I get my answer as a scalar. Okay. Does that answer your question, Anand?
Yes, it's clear.
So I'll uncomment this again. And now we have just this part. Okay. So let's implement gradient descent and see how this works out. So we say, okay, we'll go for 50 iterations with alpha as the learning rate, these many features, these many parameters. We'll start with an initial cost. So when our parameters, all thetas are equal to 0, our cost looks like this. Our cost looks like this. So we print the initial cost. Then we implement gradient descent for as many iterations. We get the value of J history and optimal parameters. We print what are the optimal parameters and we print the final cost. Okay, very simple. Let me execute this. So we say, okay, in our case, for 50 iterations when we run it, 296 is the initial cost. After implementing all these 50 iterations, we see that this is the final cost that we have for our model. For this final cost, we see that, for these final parameters, the values of theta, we need to have 14 values of theta. So this will be 14 values of theta, which are tuned exactly for our task. And now we can see that our final cost has become 11.33. So our cost started at 296. And then by updating these values, we have reached to 11.3. If you want to see the journey, that is how did these costs reduce, let us plot this. So since we have J history, that is the cost history for every iteration, we can say on the x-axis, I want number of iterations, that is the number of terms we had in J history. That given that will be on the x-axis. Y-axis will have J history, and we'll plot in red, and we'll give some labeling. So we can see that our cost starts at some 296, and very quickly our cost always travels downwards towards the number of iterations, towards 11. Can you tell me why our cost is not going further down than 11? Why is it stuck at this point?
Because it's our values so close, it's almost came flat.
Mm-hmm. Okay. No, but what I'm asking is, okay, or can you tell me the scenario where my cost can become equal to 0? What needs to be true for my cost to become 0?
All the parameters should be 0.
No. So this is not parameter, right? This is J.
Yeah.
So J is basically this evaluation. Let me go back here. So can you tell me at what value will J become 0? What should be true so that J becomes 0? Okay, this is a hint here. J will become
X
0
and Y is 0.
if Y is 0 and no, not necessary. So basically, let me tell you. Okay, J will be 0 if each of the individual error terms are 0. Okay, so this will be evaluating this subtraction h minus y, s theta of x minus y for all different samples, right? From 1 is equal to n.
Yeah.
If our prediction is exactly equal to the actual value for every sample. Okay?
Yeah.
If our prediction is exactly equal to the the true value that we have for every sample, then our cost will be 0.
0.
Okay.
Yeah.
Now, for that to happen, we also know that h of theta is a linear regression. It's basically a line. Okay. Maybe a d-dimensional line, but it's a line. Okay. Now, for this line to match with all these values should be on a line. Only if all these values are on a line, then the cost can become 0. But any real data is not that way. Any real data will have some variation. If it was truly a line for every scenario, then we would not have gone to data analytics to solve this. We would have written an equation that would have solved this automatically. So for any data science problem, it is very unlikely that you will end up with a cost of zero. Okay? You will always have some variation, some value, some minimum value of your cost, which basically says that I can never write a line that will fit all of my data. There will be some data for which I will have some errors. Okay.
Yes.
So that's it. Let us try with different number of iterations. If I go for 500 iterations, and let me also change alpha. So let's say if I go with 0.1, I can see that, okay, here also I am starting with 296. I am also ending at 11.3, and this is how my model changes. So if I keep my alpha very small, so in this case 0.001, then I can see that it takes a lot of iterations. We have crossed 500 iterations, but our model is nowhere near 11. We are just at somewhere near 125, 100. So it would take maybe thousands of iterations. So let me go for 5,000. Within 5,000 iterations, somewhere around 3,000 iterations, we have reached 0.11. So it reaches the minimum value, but it takes a lot many iterations to reach there. If we try to reduce, if we try to
Small doubt.
go on.
How effective if we change the parameter instead of zeros, if we give some other values, how it will affect?
So we are just starting at a different initial value. Okay. So anyways, we have to go with some random number. We can take anything at this point. Since we
It will affect our accuracy. It will reduce our cost.
will it reduce the? So you're saying, does the initial parameter decide what is the final cost we have?
Yes.
Okay. So for linear regression, no. Okay. For linear regression, it doesn't matter what is your initial value.
Okay.
But uh, when you go to other forms of gradient descent is something that we'll be using for neural networks as well. And for neural networks, giving all parameters as zero is a disaster. Okay, if you give all parameters as zero for neural networks, your network will never move. So to allow your network to move, you have to start with random values at every node. But for linear regression, it is not a problem. Linear regression is a convex problem. So when I say convex problem means there is only one minima.
Yeah.
So if there is only one minima, it doesn't matter where you start. You will always end up at the same location. But for neural networks, we cannot guarantee that. It may have multiple local minimas in different places. So when you start at different initial values, you may end up in different locations. So here, let us try to change this.
Instead of once.
Yeah, let me put some random number. So this is what we are passing right now, and what we want to pass is some random numbers. So let us use np dot
Random.
rand n. Okay. Rand n will give us normalized features, and
I think it's in MATLAB.
I think it is np dot random dot random.
Okay.
Okay. The tuple object cannot be interpreted. Let me. Okay. This gives us one number. Now, if I do class this first, can I give multiple values? Let's look at some examples. Okay. So not as a tuple, directly we have to pass. So I'll take this values, pass it here. Okay. So this is how we can get our random features. Let me copy that. Okay, so now we are starting with random features. Let's execute. Oh, interesting. We start with a different initial cost, of course, because now we have randomly started something. And optimal parameters, we come around 11 only, but it seems a little lesser than this. Let's try this again. Now we start at this, we end up same place. So no matter where we start, we are ending up at the same cost. Right? The initial cost keeps varying, but the final cost looks similar. Especially after 5,000 iterations, it has always reaches the same value. Let us try. Okay. I wanted to show you some more things. So this is what this looks like. Now we are going too fast, so let me reduce the number of iterations. Instead of 5,000 iterations, let me go, let's see only 100 iterations. Let us increase our learning rate. So instead of 0.2, we'll go to 0.3. 0.3 also works fine. What about 0.4? See, from 0.3 when we move to 0.4, you see our initial cost is 230, but our final cost is infinity, right? Like as good as infinity, because 1.6 into e raised to 33. It's a very high number. And if you look at the plot, we can see that our cost keeps on increasing. Basically, we have reached a point of alpha. So alpha of 0.4 is an alpha which is too big for our problem, or we are taking very large steps for our problem. Smaller than this, if we go to 0.3, you can see that yes, we are reaching minimum, and we are actually going down. But 0.4 becomes too big for our case. So this is what we were talking. I was talking about alpha. By controlling alpha, we can control how long does it take for iteration to solve. But too big of an alpha basically gives us divergence and not convergence. Let me go ahead. Further, all this is fine, but it would make a lot of sense if we could write this into a class that we can use very easily. So I create a class called as Linear Regression. To this class, we have functions like init, fit, score, predict, and get parameters. It is basically a combination of all the code that we have written so far. So in the init part, we just define all the individual terms. Alpha will control the learning rate, number of iterations as much as we want. We've got number of samples, features, mean, standard deviation. We've got a step uh, that standardizes the data. That is, and apart from standardizing, it also adds a stack of this value. That means we are standardizing the answer and then adding that additional column within this one step. Store the values, the target labels here. Initialize the parameters as zeros. Now we saw that we could do random also. And finally, create two variables as coefficients and intercept, which will store the final answer, which we are not populating at this point. Only after we fit the model can we populate this. So that is our initialization function. Followed by that is the fit function, which is basically the same function that we had in the gradient descent. So run for these many iterations. Every iteration, update the value of parameters by this equation. So new parameters is old parameters multiplied by alpha by n multiplied by this term, which is x transpose times x theta x, which is x into theta, minus y. That gives us our gradient descent. Now we are not storing the value of j because we have seen that it works well. Let us directly get the answer. Once we have the answer, the theta 0 will be the intercept value, and all other theta, that is from theta 1 to theta d, theta 1 to theta 13 will be the coefficient values. And we return self. That's it. The train function looks like this. The fit function looks like this. We have a score function that helps us to see what is our score, how good or how bad we are doing based on our y. So we are just using a score like this, which is y minus y prediction, the whole square sum, divided by y minus y mean, the whole square sum. I forgot the actual term here, but I think this metric is called as R square, which helps us to see how close we are to our answer. So maybe after this we can see how R square looks like. But this gives us a sense of score, that is what is our error between our model and our actual answer. Then we have the predict function, which is evaluated very easily. We start with the number of samples. We do the same thing, that is, we, for any new data that comes, we will standardize it using the new and standard deviation that we had earlier. Add that additional column and then multiply it with the value of theta so that we get the R prediction, that is our Y. And we are creating a function called as get params, that if we just do get params, it will return to us the parameters of. So this is our implementation of linear regression. I was interested in finding out, if we compare our method with scikit-learn's method, we can see how good or how bad we did. So in this case, I'm calling all of these things again. So linear regression as LR is our model, and scikit-learn dot linear model input linear regression. This is scikit-learn's. We are also calling train test split to get our train accuracy and validation accuracy, and we are calling pandas. We load our data, get the data in X and Y, call train test split, keep a test size of 30%. So train data will have 70% of the data, and test will have 30% of the data. We will use lr.linearregression.fit. So this is our model. That's why I call it R regressor. And linear regression.fit. This is scikit-learn's model. We call it at sklearn.regression. We check R score in R training accuracy, and we check scikit-learn's score in sklearn training accuracy. Once we have trained our model, we would want to find the score with the test data. That is R score with the test data and linear regression score, scikit-learn's model score with the test data. And we have both our accuracy for train accuracy for both models and test accuracy for both models. We finally put that into a data set, a data frame, so that we can see how it looks like. And when I execute this, we see this answer, which basically says that for training accuracy, our model or the model with scikit-learn, both are roughly similar. We are very close to each other for the training accuracy. And when we look at test accuracy, we can see that our model is doing not as good as scikit-learn's model. Scikit-learn's model is having better test accuracy, probably because I'm guessing they must have added some regularization term within their cost function to perform better. In our case, we have not done that. Still, I think we are still close enough, which basically means that we have not spent a lot of time in getting this model. Scikit-learn would have a team of multiple programmers working for multiple years to achieve that level of accuracy, and yeah, not bad. Finally, when we do X test, this is our input data that we are passing. Y test is the model's expected target output, and we will predict both cases. For our model, we'll predict the value of Y, and for scikit-learn's model, we'll predict the value of Y, and we'll write all these guys into one set, and we'll see how this looks like. Okay, so let me execute this. So this is what the output looks like. So the first value is the expected test value. So that is the label value. The second value here is P0, which is our prediction. And S here, the last value is scikit-learn's prediction. So the actual answer was 23. Our model was able to go till 28.6. Scikit-learn's model was able to go to 28.6. Okay. 32 was the actual answer here. Our model went to 36.47. Scikit-learn's model went to 36.5. So in each case, we can see that we are at par, or we are very close to what scikit-learn is trying to predict, and we are equally bad at all the actual data. Okay, so this is our implementation of linear regression. Do you have any questions?
No, we are good.
Okay. So here we did not focus too much upon our data, or we did not focus too much upon data pre-processing, visualizing, understanding the data, and so on, which we'll be doing in the next class. We'll look at this the extended version of Boston housing price data. Here we had just 13 columns. In that data, I think we have some 75 plus columns. So we'll start there. We'll look at visualize. We'll do all of our standard procedure: exploration, pre-processing, feature engineering, modeling, and then finally validation and testing. And hopefully that will reveal to us more ways, some more hands-on on data pre-processing. But that's it. If you don't have any questions, we can stop for today. Okay.
Okay then.
Let me stop sharing and stop.